Good morning, my name is Thomas Trask, and my project this semester is on using math and nature for fun and prophecy. We'll be leveraging swarm intelligence algorithms to better predict student performance. Over the next few slides, I'll give a brief overview of the background of the project's structure, and the project's results. So we all know learning is hard. Learning how to learn is even harder. Progressing from instructor-led education to individual-led education, where the instructor is more of a guide, into fully self-reliant education requires skills in time management, self-regulation, motivation, and educational path planning. Moving forward into group collaboration requires additional skill sets in self-guided research, debate, idea expression, working with others, and professional writing. These skill gaps, along with meta-educational social obstacles like family obligations, relationships, often cause many students to stumble in their educational path. So given all the issues that face students moving from one type of class to another, researchers have leveraged machine learning to predict skill gaps in students and preemptively identify student performance issues like risk of dropout, risk of failure, risk of not getting anything out of the class, using a combination of past and existing student performance, intra-course frictions such as study time, travel time, club activities, and meta-educational metrics. Traditional machine learning algorithms such as the decision trees, random forests, k-nearest neighbor classifications, and support vector machines are generally used to identify at-risk students in time for effective intervention. So machine learning is great, but it has kind of a big problem. Educational big data is big. It's got many data sets contain millions of records with hundreds of features or data points. In order to suggest the correct set of skills for a student to focus on, a machine learning algorithm needs to pick which data points are important in a data set so it can look at them and form effective predictions. Effective feature selection is an NP-hard problem, and traditional machine learning algorithms often have issues with focusing on local minima or good enough features where a more optimal set of features would be a better predictor of student performance. Missing the best set of features often leads to some students falling in the gap where effective intervention is not leveraged in time for them to be able to either stay in the class or succeed in the class. And that's where swarm intelligence algorithms can help fill this local minima gap. Because the particles in swarm intelligence algorithms spread across feature sets and can collaboratively explore the whole set, they can often find a global best feature set or solution. Research indicates that swarm intelligence algorithms can outperform traditional algorithms in feature selection, data classification, and multi-objective optimization, which can be used to give a student a number of suggestions on how to improve their performance instead of just one or two. Let's take a step back and explain what a swarm intelligence algorithm is. Swarm intelligence algorithms use mathematical models to simulate animal interaction. Using a large group of simple agents spread across the feature space, we can program the agents to communicate with each other and converge around important points within the feature space, similar to how bees converge on desirable flowers, ants converge on food, and flies converge on me every time I step outside. So let's talk about the specifics of the project. As I mentioned before, the goal of the project is to see how well swarm intelligence algorithms perform in predicting student performance when compared to existing algorithms. Because swarm intelligence algorithms have been shown to be great performance in high feature datasets, they should be better able to identify student performance features useful in targeting at-risk students. These feature identifications can then be used to help plan pre-course training for at-risk students. Because of the different set of skills required for success across the learning spectrum, we're going to directly explore the role that swarm intelligence algorithms play in student performance across three types of classes: in-person courses, hybrid in-person online courses, and massive online courses. We're going to do that by finding existing machine learning student performance research and acquiring the data that the researchers used. And because some swarm intelligence algorithms are better suited for different data sets, we're going to explore using 6 different algorithms. We'll be running the algorithms against the original data set to generate a set of features to run existing machine learning classifiers against. Classifiers such as artificial neural networks, k-nearest neighbor classifiers, decision trees, support vector machines, and random forests. We'll then be comparing these classification results to the classification results in the original research paper and seeing how they did. How we're going to do that is by creating a test harness. We're going to take in the data sets that we acquired from the original researchers, run label encoding against them to encode string data and continuous numeric data. We're then going to take that relabeled data, run it against the series of swarm intelligence algorithms that we have to generate individual feature sets per algorithm. We're going to take the filtered feature sets and run them against all of our classifiers, and to see which classifier algorithm combination gives us the best performance. As of milestone 2, we had 3 algorithms implemented: particle swarm optimization, artificial bee colonies optimization, and cuckoo search. Thanks to the NAIPy package, we were able to implement 11 swarm intelligence algorithms and cousins. We have, in addition to the first 3, we have cat swarm search, bacterial foraging optimization, gravitational search, firefly algorithm, forest optimization, monarch butterfly optimization, and the monkey king evolution. We'll be using all of these in our ensemble approach and seeing which one performs the best. Now that we've had a chance to look at the algorithms we're going to use, let's look at the data sets that we plan on using. First paper we'll talk about is the in-class paper, Student Performance Prediction with Optimum Multi-Label Ensemble Modeling. The first thing you'll notice is the giant flowchart on the right. The students did a lot of data pre-processing, clustering, scaling, feature selection, and then chunked the data set up into a number of subset data sets, ran their algorithms against the subsets, and then at the end they took a hard vote on which students they thought would pass and fail. They ended up with a 79% true positive prediction, which is pretty good, but they also found that they could shrink the feature set from 26 features to 18 features, and we end up with the same results, which is interesting. The second paper we're going to talk about is the hybrid on-campus online course. The paper is called Enhancing the Capabilities of Student Result Prediction Systems, and it uses a similar data set to the previous paper, 600 rows, 33 features. Again, the students used a number of pre-processing steps and with classification algorithms and synthetic sampling to kind of boost the representation of the failures within the class because it was so small. Most students pass a class that they have to show up for. So they did some jimmying to the data to actually be able to effectively predict who was going to fail. And they did pretty good. They got an 82% true positive prediction rate for students at risk of dropping out. The last paper we're going to look at is understanding dropouts in MOOCs. The researchers used an extremely large data set, 20 million plus records, 112,000 users across 39 courses, to create a context-aware feature interaction network to determine how impactful a student's dropping out was on their friend's likelihood of also dropping out of the course. They used the network to create a dropout prediction model with 84% accuracy. So how did it turn out? Starting with the pedagogical results, we can see that our swarm intelligence machine learning ensemble algorithms outperformed the best result from the original research paper by a significant margin. The artificial neural network that we implemented was able to achieve close to a 100% accuracy within the data set, whereas the original research paper tapped out around 79%. Continuing on to the pedagogical student performance results, we can see the same thing A number of our swarm intelligence machine learning algorithms outperformed the original research paper by a significant margin. The research paper tapped out at 92% accuracy, and ours went up to close to 100% accuracy, between 98 and 99%. Closing with the andragogical results, we can see that while our algorithms outperformed the research papers, it wasn't by much. The paper had a accuracy score of 86.5%, and ours tapped out at around 88%. Of note is that the cat swarm algorithm, the first bar in the chart, achieved a accuracy of 0.876 while only using one of the fields, the total number of interactions that the student had with the site. So that's good news. In conclusion, we can state that swarm intelligence algorithms have shown to be useful in helping predict student performance and dropout in ensemble applications, and that these are awesome, and swarm intelligence algorithms are awesome, and this project was super fun. Finally, I'd like to thank you for your time and attention, and I appreciate any feedback that you can give me to make the project more successful. Thank you, and have a good day.